My name is Maciek Buzer. So I'm one of the co-organizers, but in this workshop, we basically have four distinct themes on what we would like to talk about. And one of them, which I'm trying to coordinate, is precisely about the topic of this talk. So I will try to set out what are the objectives, what we would like to achieve, and also how these methods that are not really well known in atomistic modeling community can help and set out research agenda for the years to come. Before we start properly, I just wanted to acknowledge our sponsors. So of course we benefit from a very generous grant from ICMS itself, but we also managed to secure extra funding from three sources. So Edinburgh Math Society and Glasgow Mathematical Journal Trust. This is part of the sort of Scottish mathematics ecosystem, and they work very closely with ICMS, and we are benefiting from extra funding. And then one other thing is Mars. Mars is my research institute back at Lancaster, so I moved there in January this year, and we are benefiting from a nice grant, which I actually am going to advertise to you. So Mars is a new applied mathematics/AI section in the School of Mathematical Sciences in Lancaster, which is about 2 hours down south in the north of England near the Lake District. And basically, it's one of these structural grants that UKRI sometimes decides. UKRI is the UK Research and Innovation Agency, so the main funding body for research. They sometimes have these schemes where they essentially throw a lot of money at an institution where they try to expand capacity. And we are extremely happy to have one of these. And basically, that means 10 new permanent posts, and I'm one of them. But also quite a lot of funding for PhD studentships. In fact, one of my PhD students funded through here, Inayat, has just started and he's here with us. We have postdoctoral fellowships and also funding for all sorts of activities. So hence the sponsorship for this workshop. And I should mention that materials and maybe to some extent also engineering and chemistry has been highlighted as one of the target application areas. And I'm sort of co-leading or leading on this area. And one thing to mention, since we have quite a lot of early career people here in the audience, we will be advertising very generous, very nice, almost independent, let's say, fellowships, which are 3 years, and they will be advertised later this year. So if you finish your PhD or are close to finishing and have some, independent research agenda you'd like to develop, please apply. We would love to have you. And, if you want some information informally, please approach me during the coffee breaks. Yes, okay. Right, so let's move on to, maybe I'll go here. I shouldn't. Okay, so my talk is about continuation and deflation methodologies. And let's start with some motivation. So as you all well know, many nonlinear models of physical systems have multiple equilibria. And at least in principle, a lot of the properties of the systems can be inferred by kind of trying to map out all these critical points of the system. And a lot of things go into it. So first of all, you ideally like to find all the critical points, or as many as possible. Then maybe also identify the basin of attraction, meaning that if you do some gradient descent from a given state point, you will then descend to one of these critical points. Then all these critical points are somehow connected to each other, right? So I will give you examples of that later on. But somehow you'd like to assemble some sort of network of equilibria. So for instance, if you have two local minima, they might be separated by index one saddle point, and so you can create a graph of connections between critical points. Then you can, in a lot of models, you have parameter dependence, so you can try to understand how these things change as you adjust parameters. And in the case of atomistic systems, we, of course, especially if we model them with interatomic potentials, which I'll explain in a second, the potential energy landscape, obviously it just tells you about the most likely arrangement of atoms, so stable and maybe metastable configurations. Index one saddle points will give you transition paths between the states. And there's a lot of associated physics, so we have quite a lot of computational material scientists here who really, and physicists as well, who can infer real science from this pretty abstract framework of mapping out the landscape of the associated problem. And in atomistic modeling, of course, this is an extremely important and fundamental problem. So there's by now a lot of standard tools. And here's a list that maybe not exhaustive, but quite, probably most of you have heard of these. So first of all, of course, we can do molecular dynamics, which is essentially you allow the system to evolve, you add some temperature, atoms vibrate, and then every once in a while, through random vibration, they will escape the basin of attraction and they will go to a different one. And then you have some algorithm which detects this change and tracks it. And that's how you find new critical points. Of course, once you detect that you went to a different basin, then you can also do relaxation, which is just energy minimization. And then you find the minimum that is in that new basin. And then typically you run what's called the natural elastic band calculation, which is you have two supposedly neighboring minima. This is a standard algorithm which allows you, in principle, to find the index one saddle point in between them, so allowing you to make that connection and this graph of all the critical points. Then there's other methods such as Dimer method that essentially is a method where you start from a local minimum and you try to find index one saddle points. So these list resistant barriers to going to different basins. And then there's connecting to parameters. You can do something called quasi-static loading. So you identify some loading parameter, you increase it or decrease it, you relax, you detect an instability. There might be a sudden big rearrangement of atoms. And then potentially you can try to go back then and maybe try to reverse the changes, and then you have something like hysteresis loops. And slightly related to that, but maybe less important for materials, there's also, where do you start from? Because, once you have one local minimum, you can do all these things. It will give you some local information, but there's always the question of, like, maybe, there's some other parts of the state space that are completely not connected to your problem. So then you would like to have as many starting minima as possible. And there are some techniques for that. And there's a quote that I quite like from this book from David Bowler about atomistic simulations. There is no simple prescription for this problem. It is one of the most complex problems in physics, chemistry, material science, right? And of course, these methods are extremely popular and extremely powerful, but there are some limitations. So I maybe mentioned all of them a little bit already. So of course, they are quite local in scope. You start from some minimum and you basically build your way up in this graph. And really, there is no guarantee of any sort of completeness, especially if you have a system of a lot of atoms. It's so gigantically dimensional that you can never really know if, have you run MD for long enough? Is there some sort of unconnected part of the graph that you haven't explored yet? And there's really no simple tool to even quantify level of completeness, local completeness even. Generally, when these instabilities or sudden rearrangements happen, when you change the parameters, the Hessian of the energy is singular, so there's some mild headaches there. I will also briefly discuss, and we'll hear it throughout the workshop, that, for instance, natural elastic band can be very sensitive to. So natural elastic band has some parameters within how you calculate. You try to find these index one saddle points, and essentially, in some setups which we will discuss, we can essentially say that it's completely arbitrary what NEP calculations give you, and all that essentially contributes to the fact that these connectivity graphs of equilibria are hard to assemble. And of course, if you have an extremely complex landscape, all these issues are even more pronounced. Okay, and so there is a set of tools which can help, has not really been explored that much in this setup, and there's good reasons which I will touch upon. But at least in principle, these two methods, which I'll explain in a simple detail, they are well-established techniques for handling general nonlinear equations. And in atomistic modeling, they can offer complementary perspective to all these standard tools that I discussed. So we could have a systematic exploration of equilibrium branches. Here, I mean, you basically pick some parameter and you vary that parameter and you have a continuous curve of solutions. You can detect bifurcations. So these instabilities that I mentioned in this framework that are quite easy to handle. There would be, improved local searches for saddles and nearby minima, which I will touch upon. And we could even, when the instability happens, we can maybe even talk about deterministic causality. If a lot of rearrangement happens in different parts of the material, you can still untangle it with these tools. And generally, especially combined with all these standard tools, because I don't want to, they are amazing and they should be used, but using them can be a foundation for maybe slightly more complete landscape mapping. And as I said, they have been largely overlooked in atomistic modeling, but there was a white paper from IPAM program. IPAM is an institute at UCLA, a bit like Newton Institute here in the UK, where we spent 3 months looking at different aspects of high throughput atomistic simulations. And there is a conclusion there that trying to develop these tools, especially for atomistic simulation, is desirable. Okay, and so precisely just to give you an overview, so in this workshop, we're trying to bring together researchers recently developed or applied such tools in atomistic modeling. I think we managed to get almost everyone, barring maybe some last-minute cancellation, but we'll see. We also invited experts on continuation deflation techniques in other areas, so not connected to atomistic modeling, to tell us about their perspective. And maybe, try to get them involved in trying to tailor them to atomistic setup. Also, there's just the idea of advertising such work because, as I said, it's quite niche. So, it's nice to bring together everyone and discuss results. And there are some inherent difficulties with this problem in atomistic modeling. And we will also, of course, like to, facilitate new collaborations. For instance, maybe there's people working on atomistic modeling that struggle with the classical toolkit. Maybe NEP calculations are not good enough. We should talk, and maybe we can use these tools to see if maybe we can solve your problems. And of course, with we'll see, but maybe in 10 years time with a broader adoption, let's say, these tools will be on the standard list of tools, which of course at the moment they clearly aren't. Okay. Okay, so rest of the talk, we'll have quite a bit of time. There'll be a very brief primer on atomistic modeling with interatomic potential, because there's some people here who are maybe not familiar with it. Then I'm pretty sure there's at least a portion of audience that doesn't really know much about continuation deflation. I'll discuss that in a very toy model setup. And then I'll mention some of the applications and showcase and advertising the other talks at the workshop that are related to it. And at the very end, I'll also discuss some possible directions and discuss the issues that we face to make it a reality. Okay, so for people who don't know much about interatomic potentials, here's a very simple slide on trying to introduce it. I'll also set out some notation. So typically we are interested in modeling d-dimensional, d being 2 or 3, system of atoms occupying some positions. In computation material science, we usually use capital R, bold capital R, to refer the configuration of all these n atoms. Then each atom is a little r, bold R. This is a d-dimensional vector. And ultimately, we're after modeling it with some atomistic energy, which for any configurations of atoms just gives you some number. And typically, this is done in the so-called body order expansion. So what you do is you essentially first look at simply positions of atoms themselves. So that would be E1. This is typically related to external forces. So for the sake of this talk, we can set it to 0. Then the absolute standard, well-known thing that's been going on for the last 100 years, I guess, is two body forces, where you really just do a double sum over every atom and just check what's its relative position to all other atoms. And typically, these two body forces, all they care about, because we have some inherent symmetries in the system, all they really care about is the distance between the two pools of atoms. And there are a lot of standard potentials, empirical interatomic potentials, such as this one here. This is the so-called Morse potential. It has just 3 parameters, and I'll show you what it looks like on the next slide. And the point is, now these days we have the revolution of machine learning in this field, where essentially you ramp up this order to say 4 or 5. You use some simple functional forms, but with an awful lot of parameters. You fit it to some electronic structure calculations from quantum mechanics. And that's supposed to be extremely, way more accurate than the empirical potential. And of course, it's true. But, you know, that brings its own set of problems, because essentially, if we want to develop these tools, we don't want them to be just a mathematical curiosity. Any algorithms that we develop, they should be compatible with the infrastructure of these machine learning interatomic potentials. But really, in this talk, we will only ever use this simple potential. So we truncate the sum at 2. And here is how this potential looks like. It's very typical of any interatomic potential, and probably have seen things like that before. So generally speaking, atoms absolutely hate to be very close by. This is due to, you know, cloud of electrons. There's some repulsion forces there. So a lot of these potentials essentially blow out to infinity. In fact, Morse potential doesn't, but it is extremely steep. Then, generally speaking, if you just think of 2 atoms, there is some preferred distance where they're happy to be apart. That's that minimum here. And one of the parameters in the potential can change that. As you can see here, the A3. And then there's a generic rule that if 2 atoms are too far apart, they cease to feel each other. And that is reflected by the fact that the potential just plateaus. That means that, you know, first derivatives are 0, so there's no change in, and the, you know, energy stays constant as well.
I'm sorry, could I ask a dumb question?
Yes.
Yeah, could you go back to the previous slide, the picture? So that your picture looks like there are singularities as r equals to 0, right? But I don't quite see that in this formula. Where
yes, so no, the Morse potential, there's no singularities, but there is a more archetypical.
This is just an example. I mean, no, so that was the realistic potential you were showing us.
No, Morse is still not realistic.
No, I mean the picture you were showing us.
Yes, this picture is literally this formula for different values of A2 and A3. A1 is just a prefactor. We don't really care, at least as mathematicians, about A1. But this is how it looks like. I mean, it doesn't, the singularity doesn't really happen here, but it gets extremely steep near 0.
I got confused. And how do you choose the K again, did you say? This big K?
Ideally, you'd like it as high as possible.
Oh.
So in the past, empirical potentials, they would mostly truncate at 3, and there would be some heuristic physics arguments about what should be the functional form, and that would be it. Whereas now with machine learning potentials, you basically, you have some generic ansatz, which is maybe a little bit motivated by some symmetries, but then you just feed it to data, and essentially you try to do the framework learn these kind of 5-body interactions from data from quantum mechanics. So, but in practice, I believe, and there are, you know, experts here on this topic, I think you stop at 4 or 5.
Oh, sorry, if I could just ask a little bit more.
Yes.
In that potential, I mean, some atoms are attracted to each other, right?
Yes.
So why are you just showing a singularity when they go
to
each other?
I mean, we're mostly thinking of atoms of the same species.
The same species. I see. Okay, so that was my. Okay, that's fine. Yeah.
Okay. And then just one slide on statics and dynamics. So we have this energy, and then we can compute derivatives. So we can compute the derivative, which is with respect to some atom. This is a three-dimensional vector. Forces are typically negative, the minus of the gradient. And when we say about critical points of this energy or equilibrium configurations, it's simply all the possible configurations such that the forces are zero. And then in dynamics, we have Newton's law of motion. We can introduce auxiliary velocity variable. We have this equation here. And in practice, there's a lot of work about discretization. You might have a scheme like that. And the whole point of MD really is that you, of course, introduce some stochastic fluctuations due to temperature. But if you set temperature to zero, then that would be the equation that we'll be solving in time. Okay, I mean that's maybe mostly for people who haven't done MD at all. And when I try to explain what continuation and deflation is, especially to computation material scientists, I lose them. So here's yet another attempt, and this is really the easiest I can think of to try to convince. So please let me know if that's obvious enough. So let's say we look at a system of atoms which is arranged in a square lattice, and let's say we freeze all the atoms in there. So all the atoms in black are essentially like a boundary condition. They're just frozen in time. We don't touch them. And to make it non-trivial, normally we have a defect in lattices called the vacancy, which essentially means that you have perfect lattice, but then you have one atom missing. And for the purpose of demonstration, it's actually more useful to have two atoms missing, because then the underlying potential is showing me what I want to show you. But this is completely made up. And the point is that technically you still have that atom here. And let's allow it to move around. This is the only atom that is allowed to move around. Also, this is 2D. So really, you just have 2 degrees of freedom. And so you can check the landscape and plot the contour plot. And this is really the landscape. I admit that to make it a bit nicer, this has been stretched. But really what you're seeing here, any point here in this landscape corresponds to the possible place this atom can have, right? So for instance, if it starts here and you move it to here, this is your point in the energy landscape. Okay, and I am actually computing this potential. Except of course, I constrain all the atoms to stay, all the atoms in black to stay where they are. So then you can check, because it's all 2D and very simple, that you basically have 3 critical points, at least within the region that you allow the atom to move. There will be a local minimum here, which is essentially the reference position. There will be, by symmetry, there'll be another one there. And then that guy here, where the other missing atom is, it can actually be checked that this is an index 1 saddle point. Okay? And I'm just setting the scene. I'll come back to this example later to actually explain what deflation and continuation does. But this is just the basic setup. And you notice that here, this landscape has been shown for A2, one of these parameters in the potential, is equal to 5. And now I start changing it. Now I change it to 4. The landscape is slightly different, but as far as critical points are concerned, they are still exactly in the same spot. I can adjust it even more, 3.5. It essentially gets shallower and shallower, but as far as the critical points are concerned, it's still exact same. So let's go back to 5 and let's try to make it non-trivial. And one way to make it non-trivial is to add fluctuations. So I now displace all these atoms, added some random noise to their position, but they are still frozen. Okay, and the setup is still exact same. And now the energy landscape is different. So I mark here, this is the possible reference positions. The orange dots are the missing atoms. And now, as you can see, at least for this value of the parameter, you actually now have 3 local minima, one here, and one here. You have two saddle points separating them. And in fact, this guy seems to be extremely shallow in general. And I can repeat what I did just before. So I can now start adjusting this parameter. And as you can see, these two critical points get closer and closer. And eventually for some critical value, they collide and disappear. And that would be like the instability that you observe in your simulation. Okay.
Sorry, I have a question. So
Yes.
on the axis on the left, you have going from -2 to 4, but on the right, you have a delta x. So that's not position.
Sorry, yes. So that's inconsistency. It's with respect to the reference position. So you'll notice that this reference position is at 0, 0. But other than that, it's all perfectly consistent.
Okay, great. Thank you.
Okay. And you know, the point is that after the collision, you can still change the parameter, and essentially, you know, once it disappears, it disappears, and you know, landscape looks like this. Okay, and then and you know, that's not the only thing you can do. So let's go back to 5, and now let's try to think how else we can influence the system. So for instance, we can take that atom here, and we can start moving it. Okay. And because it's part of the boundary, it changes, you know, it influences the system, but it's like an external thing that you can do. And so if I do that, you notice that these two guys kind of get closer together again. However, you know, by design, I had to tinker with quite a lot to get that, but essentially you'll see that in this instance, as you move this atom closer, in fact, it's these two critical points that collide. Right, and then that saddle is still there, and presumably the other local minimum is somewhere here outside. Okay, so that's not a continuation deflation. This is just how changing parameters can influence the energy landscape. And one thing to remember here, of course, this is a complete toy model for 2D. In practice, we're thinking of atom, you know, thousands of, if not millions of atoms, but the principle is the same. Okay, and so now continuation parameters are essentially precisely what I showed you. I gave you two examples. So in general, we start with this function. We identify some parameter, which and we basically treat it as a variable in the system. Typical examples is you pick some function of parameters of the potential. For Morse, I just picked A2 because it's the only interesting one. You can have a loading parameter or some other boundary condition approaches, and arguably even this guy is sophisticated in the sense that I spent half an hour thinking what is the plane, which atom will give me this, you know, behavior that I want to, because I really wanted, you know, a different critical event to happen. Okay, and other thing which one of the talks will mention at this workshop is some biasing force acting on some of the atoms. And I basically alluded to this already, but you know, during this procedure, we can switch from one parameter on the fly to the other, or even consider multi-parameters. So where mu is now more than the vector, p-dimensional vector. In practice, going beyond p equal to 3 is quite difficult. Okay. And so what's the point? The point is, you know, a standard kind of bifurcation theory or continuation theory that dates back to the, say, 60s, 70s, maybe. The whole point is that, okay, we had these forces. We basically have some reference parameter. And let's say we have some configuration, which is already typically a local minimum because you have some solver that lets you relax under the potential. And then the point is that under some conditions, you have implicit function theorem, which tells you that as you change this parameter a little bit, you will locally have a locally unique curve of solutions. And in general, you wouldn't, so here the parameterization is by the parameter itself, but to give us more flexibility, you want to introduce some parameterization parameter or arc length parameter, a bit like when you trace a circle, you use the angle theta, and that allows you to trace the whole circle, whereas if you parameterize by one variable, you would essentially just be able to trace half a circle. And you typically add some unit speed parameterization. And then the whole scheme is you have one point where forces are 0. You treat it as a abstract point in dn plus 1 dimensional curve. You compute the tangent with respect to the parameter, which you can write down an equation or you can approximate it, and then you solve this extended system, which now works in this dn plus 1 variables. So you need to close it with an extra equation. And ds is some parameter that to say how long along the curve you want to go. You can visualize it like that. So you have one point. We would like to trace this green curve. What we do is we compute the tangent. ds is the parameter, how long along this curve I want to go. And this final equation is essentially telling me I want to go in the perpendicular direction to the plane, the tangent plane. And hopefully, that nudges it towards the curve. And especially if ds is small, you're so close to it that you are quite easily able to find the next point. And it's this picture where I typically lose, especially computational material scientists, about like an abstract curve in dn plus 1 dimensions. So let's go back to this toy example. So this is the old plot where, because it's so simple and low dimensional, I can just track all the critical points. But remember that with continuation, you basically start with one minimum. It's that red dot here. You pick some parameter. That should be A2, sorry. And then T0 would be the magnitude of the displacement of that atom. So for the sake of this demonstration, I will keep it at 0. And I run this algorithm. And you see that A2 now decreases. And you remember that there will be this collision. And that's precisely, we are just tracking this curve. Nothing interesting happens until they collide. And what happens then is, instead of kind of annihilating, this curve turns around. So you'll notice that now A2 starts increasing again. And we basically jumped from tracking the local minimum to the saddle point. Okay, and it just continues. We are now tracking for some values of the parameter, we track the saddle point. And the point is that it's just as easy as tracking the stable branch. So we have a very flexible algorithm for being able to track these saddle points, especially after they collide with a local minimum. And I think the key point is that you can go back to your reference value of the parameter. So, I mean, it's not quite here, right? But if I was to do some bisection, I could set alpha or A2 exactly back to 5 where I started. And that means that I still have the exact same system as I started with, for people who just don't want to touch any parameters in their simulation. Okay, and that's it really, right? The basic point of continuation is that. Of course, as I said, I'm not going to be showing it here, but you could do the same with T0. So you could keep that as a parameter, start from this guy, track this collision, turn back, and basically you explore two saddle points nearby. And of course, the whole point is that this is just a different perspective on the standard toolkit, and where you would run MD, and of course after if you start here with enough MD, you would probably fall to here. However, even in the simple case, the point is that these two guys, they're so shallow that MD, you could basically, if you add too much thermal stochastic noise, you might essentially mess it all together because it was so flat. Okay, so and now let me just state some magical facts about continuation, at least in the context of atomistics. So this extended system, even in this instability, it's not singular at all, because we actually capture the singular mode, the eigenvector corresponding to the 0 eigenvalue, and we basically add it in, and it regularizes the system. And so traversing the instability is not a problem at all, at least in principle, unless it's extremely sharp. However, we have to use a root finding algorithm. We just look, this is a nonlinear system of equations. We have to solve it. There's no energy that we minimize. And a lot of people, the sophisticated algorithms for minimization. But there are some sophisticated algorithms for root finding and all these clever tricks, such as, limited memory, BFGS, or conjugate gradients. There is a counterpart to that for root finding. Other thing is we can detect changes of stability without ever computing the eigenvalues of the Hessian, because typically this, as soon as you see this change of sign of the parameter, that in almost all cases tells you that change of stability has happened. And in a generic setup when there's not perfectly symmetric system, and that's, I guess, what we would like to target as well. These bifurcation points will almost always be a simple fault point, meaning that you simply have two guys colliding, and then the algorithm would just go back and start tracing saddle points. D is small enough, if you compute the tangent to the curve, then and you move a little bit, tangent essentially tells you all you need to know. So there's even an extremely basic insight that you can, if you have these quasi-static simulations, using a tangent information accelerates them enormously. To be able to be compatible with modern machine learning potentials, you really don't want to do Hessian information because it's extremely costly to do it. So we basically try to devise a gradient-only scheme. And that basically means these tangents and a few other computations, they are done with finite differences with respect to the arc length parameter. And as some of the talks this week will highlight, this seems to work extremely well for even extremely complex landscapes with these machine learning potentials, where really if someone asked me that 2 years ago, 3 years ago, I would guess, that's the limit, this will not work, but it works.
Why did you expect it not to work?
For instance, because these machine learning potentials, they sometimes struggle with smoothness. So you will suddenly have a tiny jump, and that essentially kind of kills. Underlying all this is assumption of some smoothness of certain order that allows you to have it nicely tracked. That's one thing, and the other is fine. In a very complicated system, you have this bifurcation. You go on the unstable branch, but then there's no guarantee that it remains important past. You start going back, and maybe some other bifurcation almost instantly happens that takes you to a part of the state space that is not relevant to your simulation. So essentially, enormous complexity. I just thought we would just have a lot of data that's meaningless to the simulation, and it's not, it ends up not being a practical tool. But at least in one case, which I'll get to, it requires further tinkering, but you can get it to gain some information. Okay, I'll speed up. There's also deflation, and there'll be talk by Patrick Farrell, who is the expert on deflation techniques in the context of PDEs. Very briefly, the idea is if you have a, say, polynomial, and you'd like to find all the roots, let's say you have one with some numerical scheme, then you can deflate away that monomial and look at a deflated function and rerun your scheme, and hopefully by iterating that, actually you will eventually recover all the roots of your polynomial, or in higher dimensions, maybe the equations for equilibrium equations for setup of atoms, configuration of atoms. And the basic point is, again, you have these forces. We found some configurations of atoms, and then we apply what's called the deflated residual or deflation operator MP alpha. P is just so you basically add something that will blow up to infinity when you approach the known solution. One of Patrick's insights was that in the context of PDEs, or maybe in our context, adding some alpha also regularizes things. The issue there is if you do that, even if your Hessian of the energy is sparse, which would be the case in interatomic potentials because atoms only interact in some neighborhood, naively applying this guy would mean that this f, which, so you know, the derivatives of g, the Jacobian of g would end up being dense, which I guess at least in some sense kills the idea of it being practical for atomistic modeling. But in the past, you know, there's a healing idea of basically trying to localize this operator. So maybe just look at atoms in some neighborhood, but nonetheless, you know, it blows up if the atoms in the region that you're interested, they are at the exact same configuration as you have already explored. And in fact, Marcus' talk on Thursday, he's the person who looked at these localized deflation operators just in general context of optimization. So he will, part of his talk will be about that. And what would it do in our toy problem? So deflation always works with some initial guess. So before applying deflation, let's say if this is our initial guess for the equilibrium, we just do a gradient descent. Of course, we will identify this guy, the local minimum, for which this is still in the basin of attraction. And then we apply the operator. And just by changing p, so if you apply it with the exponent 2, the same algorithm starting from the same starting point will now identify this guy, so already a saddle point. But now, just for the sake of it, I started changing it, and it turns out that for p 1.2, you'll find this saddle point, which, you know, again, it's a very shallow thing here. So it's interesting that it's able to pick it up. And somehow, when it goes even lower, it will identify this guy. Okay, so again, low dimensional, and I hopefully managed to keep you all being able to follow. The point is, it's in the toy problem, these two approaches essentially allow us to explore all there is to explore. But of course, you know, the challenge is to do it for the full thing.
So Maciek, very
Yes.
quickly, what kind of alpha are you taking here?
Tiny positive. I changed it, but nothing interesting happened in this problem. Okay, and I would just briefly go through applications, because in fact there'll be talks about pretty much all of these applications. So we started looking at it in atomistic crack propagation for brittle materials. In these cases, you often have boundary conditions from continuum elasticity with a prefactor k, that's the stress intensity factor. So you basically constrain all the atoms apart from the purple atoms to follow this displacement. We have to tinker a little bit with boundary conditions, but eventually we use that k as a continuation parameter, and we end up observing these curves, which are what's called snaking curves. So this is the stable segment. You reach some instability, but then you turn back. These are the saddle points. And then you're back on the stable branch, and the crack is propagated by one lattice spacing. And you can check that these are in these saddle points because you can redo the NEB calculations, which you would normally do in this case. So these are the NEB curves, and the dots are actually the values of the saddle points that we computed, and you can check that these are exactly the saddle points. And you can also have plots like that. That's for a toy model, but then we also applied it for realistic, or what was at the time realistic potentials. So two empirical potentials called Kumagai and Tersov. So these are empirical up to 3-body order, still inspired by physics in some way. And we do it for silicon. And you know, the configurations hopefully kind of show that you do track propagation, because compared to here, the crack has propagated by one lattice spacing. And the point is that it's perfectly easy to capture that instability, turn the corner, run through it, or even, you know, identify this really funny inflection point on the unstable graph. I should mention that there was some prior proof of concept of Chantal Li about 12 years ago now. Then I entered through my PhD, where we looked at more sort of numerical analysis aspects. And then we also recently, with Julian, who will be talking on Wednesday, I think part of this talk will be devoted to that. You can think about better boundary conditions where you do some sort of expansion in K as well, and you solve some PDEs. And then recently, Lakshmi, who's here and is going to talk later today, actually, there was the idea that now, you know, we should use machine learning interatomic potentials, and her PhD thesis was in part devoted to doing that, and also thinking of a sort of proper 3D setup. Is that correct? Okay, I mean, actually, we'll tell you about it later today. And also, I presume some part of James' talk on Friday would maybe also touch upon these things. Okay, I'll briefly just go through other ones. So we did some prototyping with some people. So Tom Swimmer was supposed to be here, but unfortunately had to cancel. And Danny's here, and Danny's postdoc Sumendra, they looked at dislocation nucleation. I just have some pictures. Essentially, these are copper atoms. If you do quasi-static, you basically see change of stability like that. But if you do continuation, you are able to perfectly track nucleation of a dislocation and movement of it through the material. More importantly, so this is periodic, so it's thin. So the dislocation is really just a line, straight line. But if you make it thicker, and it's so thick that you need to really stop visualizing the atoms to see. With this very prototype-like algorithm, we are able to trace unstable branches which look like this. These are the dislocation curves, and as you increase the parameter, they appear to be merging. But you know, it's already quite interesting that it's not just one loop. Maybe it's even some issue with the algorithm. This is just very prototype work. Other thing was vacancy migration. So this is a very simple setup with two species atoms. You adjust the parameter, and you see that there's a vacancy here. You end up on an unstable branch. You start to see that the vacancy is migrating. So you traverse the curve, but there's still some disorder. But if you go back to the reference parameter, you end up with still pretty perfect lattice, just as before as we started. But you know, this is precisely the saddle point where the vacancy is trying to move to a different spot, and this tool finds it very easily. And then, you know, as you go further, it generates into big mess. So it's almost like a phase transition as well. Okay. We can also, and this is maybe the most non-trivial application of it, and Fraser will about on Tuesday, we can try to tackle some issues about avalanches and materials, or in this case, an amorphous carbon. So in amorphous carbon, you do quasi-static simulations where you are just loading at the boundary, and every once in a while, you suddenly have a flare-up of activity. So all these atoms have rearranged significantly enough for the algorithm to flag it up. And the issue is that people in this community struggle to disentangle what are the constituent events of this, what's called an avalanche. And, you know, this is a big thing in a lot of physical systems. And with continuation, and I'll leave it to Fraser, we can really, you know, isolate them like that. So these are actual equilibria, right, that we are able to capture. And we can also, with some tricks, talk about causality. So for instance, which of these constituent events actually triggered the avalanche and things like that. And finally, I'm really happy that Subu is here. So Subu, his PhD thesis 11 years ago now, attempted to use these tools to really do a full mapping of the energy landscape for a simple system of 104 atoms. And it's highly symmetric. And it's nickel nanoslab in uniaxial compression with embedded atom potential. And if you really try to, you know, it ends up being, even for this tiny system, you end up with 8,000 solution segments. And that was done over 2 weeks, right, on a parallel cluster. I mean, back then, you know, maybe now we can do it much faster. But the point is that there has been some really nice prior work on applying these tools. Okay. Nearly done. You know, we can talk about it all throughout the week, but really, I'd like to, you know, my thesis here is that these tools should be developed, and there's some nice aspects of it. So first of all, they are embarrassingly parallel in the sense that you can run these simulations completely separately. Many many instances, and you just, track the curves, you track the bifurcation, and maybe you only stop the simulations once you go back to the reference parameter that you were interested in, and only then compare with other simulations. This idea of not trying to get away with just gradient information could be considered a modern twist on these continuation bifurcation theory tools, because we need to, if you do this finite differencing, there's issues at turning corners that can be overcome if you're clever. So really, it's more like thinking I cannot access Hessian information. What can I do to make it work? That's the kind of modern twist on bifurcation theory. We have a prototype wrapper around LAMPS, which is the go-to molecular dynamics simulation. Conceptually, it would be easy to add it natively in LAMPS, and in fact, I did talk to Aidan Thompson, who's one of the developers. He would be sympathetic to at least listen to us if that could be added to LAMPS. There's been some recent work by Tom, which is a really shame that he couldn't join, about related topics on implicit differentiation within LAMPS. And really, I think the point is that there's a lot of setups where the standard toolkit is either a headache or it doesn't work at all. I would love to hear about these setups, and I'm always on the lookout for new test cases to try to see if this set of tools can help. And some ideas, for instance, can be a benchmark for completeness of, if you assemble your network of equilibria, if you want to check if it's complete, just start a simple continuation with some simple parameter for all of them. Do the turn, do the traverse the bifurcation point, go back to your reference parameters, stop all of them, and check how many new equilibria configurations you discovered compared to what you had already. And that would be a benchmark for how complete your prior method was. We also played around with the idea of maybe a deflated dimer method. So you found one saddle point, can you find others? There's also some interest in continuation of the unstable eigenvectors. Also, of course, you should combine it with standard tools. And even, with the AI and LLMs and everything, you could conceivably maybe think of some really automated framework where you essentially ask, develop a system where it automatically runs all these simulations. And in fact, the toy example that I showed you today, I basically, ChatGPT gave me all the code for it. I mean, I had to spend a lot of time to get it what I really wanted to, but it knew when to stop and so on. So at least as a proof of concept, if it's possible. Finally, I'm really done. And I touched all of it on a lot of it, but being restricted to first order means that we cannot use some of the methods, additional methods, branch switching, adaptivity, trust region move. It's so much easier if you have Hessian info. For deflation, I already touched upon. We really would need to tackle this loss of sparsity somehow in a reliable way to make it compatible with modern approaches. Picking and mixing of parameters is an art. So, maybe this AI tool would automate that. It's also a headache to have a really robust HPC. We really want to target real simulations here. And lastly, I do think that it's a huge bottleneck to try to popularize these, because I think NEB and even dimer method are far more intuitive, and there's good, efficient implementations where especially practitioners don't really have to think about it, they just use them. And my experience is there's a lot of effort to convince people that it's worth their mental effort to grab these tools. So hopefully maybe at least, the very simplified setup today was simple enough to convince, to give you a gist of what these methods are about. But it is my experience that a lot of practitioners just cannot comprehend what's going on with these kind of verification and switching, going to the unstable. Okay, and basically, I think said all of that. So thank you very much for your